Okay, so a little bit of review from pre-calculus or calculus A is how do we convert from parametric to rectangular? We saw a lot of the graphs were parabolas, so is there a way to show that in rectangular form that it actually is parabolas? Okay, so let's just look at a couple examples. Each one kind of has its own trick. For the first example, let's take a look at the equations that we had, which was x is equal to 1 over square root of t plus 1, and y was equal to t over t plus 1. This was the last graphing example that we did. The strategy here is actually to isolate t and substitute. Okay. So typically the best place to isolate the t is over here in the x. So I have to do a couple things before that's ready. I'm going to square both sides, so I get x squared equals 1 over t plus 1. I'll cross multiply, so I'll get t plus 1 equals 1 over x squared. And then I'll subtract the 1, so t is equal to 1 over x squared minus 1. I'm going to take this entire jobby and plug it in wherever I see a t, which would be here and here. And what you'll notice is now instead of having y as a function of t and x as a function of t, I can just rewrite everything y as a function of x. We may want to clean this up a little bit by using lowest common denominator. If I combine this, this becomes 1 minus x squared over x squared. Maybe that'll help us out. So I'll plug that into the top, 1 minus x squared over x squared, all over that same thing, 1 minus x squared over x squared plus 1. Okay, with a little bit of simplification, you'll actually show that y is equal to 1 minus x squared. You would think you're done, but if you remember the graph from the previous example, the graph actually has some domain issues and it never went over here to the negative side. So you have to account for that. How do you account for that? Well, notice that t has restricted values because of the square root, and so you just have to kind of either graph it or test the values, but you can actually show that the domain is x has to be greater than 0. And the reason for that is x, first of all, can never be negative because I have a positive square root, and even as t goes to infinity, x gets smaller and smaller without quite getting to 0 until you arrive at infinity. For our second example, let's bring trig in. So let's do x is equal to 3 sine theta. If the theta makes you uncomfortable, you can just replace it with t, and y is equal to 2 plus 4 cosine theta. If you use the same strategy as before, you're going to get something that looks like theta equals arc sine of x over 3. That's actually a mess because you have to deal with domain issues. So we don't want to use that strategy. What we want to use instead is we want to use trig identities. Okay. So the trig identity that we'll use in this case is sine squared theta plus cosine squared theta is equal to 1. So we have to isolate sine theta here and cosine theta in the other expression. Well, sine theta is just x over 3. So that means sine squared theta is x squared over 9. And on the other side, if you do a little bit of algebra, you get that cosine theta is equal to y minus 2 all over 4. So cosine squared of theta is equal to y minus 2 quantity squared all over 16. So now all it takes to write the answer is add this and this, set that equal to 1, which is the same thing as adding this and setting that equal to 1. So our rectangular form looks like x squared over 9 plus y minus 2 squared over 16 is equal to 1, where if you're a good Algebra 2 student, you should recognize that that in fact is the equation of an ellipse. So you can graph this on your calculator to check if that's the case. Here's another situation where you have to use a few tricks or some trig identities. Sometimes it's obvious, sometimes it takes a little bit of thinking. Let's say x is tangent of theta and y is cotangent of theta. So what would this look like? The most obvious one you can use is that tan of theta is just 1 over cotangent of theta. Or better yet, you can say tan theta times cotangent theta is equal to 1. So I just need to solve for tan theta there and cotangent theta there, but it's not difficult because tan theta is already solved for, and you can show here the cotangent theta is y over 2. So if I multiply this together with this, so x times y over 2, that should just give me 1. and you can rewrite it as xy equals 2, or if you want, you can write it even as y is equal to 2 over x. Okay. Are there domain issues? Well, I'll let you think about that.